It is incumbent upon every visionary and every practitioner of technology to ensure that future generations have a home. Humans are not the problem. Hubris is, greed is, complacency is. Now is the time to leverage what we know for the benefit of posterity.
Welcome to the Friends of Space Resources podcast, a place to explore space resource exploration and utilization. What is it? Why it matters? And why it's so vital to the future of space investigation. Each week here, we'll meet with a technical expert in the field of space resources to better understand and gain deeper insight into their field of study. Welcome your host, Valerie Eastman.
Okay, hello. Welcome to this episode of Friends of Space Resources. I'm Caleb Eastman, standing in for Valerie Eastman. Every week on our program, we host an expert in either space resources or related fields. Sometimes our guests are not directly working in space resources, but specialize in a relevant field here on Earth or otherwise. In order for space resources to become a reality, we have to engage experts from a wide variety of disciplines. Really excited today. My guest is Jason Henning. Jason is a phenomenal scientist. I'll let him give you his background. And what I'm going to do is I'm just going to ask Jason for you to just give us your background. I'm particularly interested in talking about your work on the South Pole Telescope and anything relevant there.
Sure. Yeah. So my background is in observational cosmology and some instrumentation. So I worked on, as Caleb just mentioned, the South Pole Telescope. We were really interested in looking at the leftover light from the Big Bang, sort of this afterglow light that's been streaming through the universe ever since the beginning. It's now very cold microwaves. And if you study this very carefully, you can get really interesting information about the very early universe. So because it's microwaves and because it's so faint, you have to do some special things in order to observe it. And it turns out microwaves like to be absorbed by water. While your microwave cooks your food, it's the water in your food that's absorbing the microwaves in the oven that heats it up. So if we want to look at the CMB, the cosmic microwave background from Earth, you want to go someplace high and dry, away from as much water vapor as possible. And it turns out that Antarctica is one of the driest deserts in the world. If you go to the geographic South Pole, not only is the air very dry, so there's a little less water vapor there, you're also a couple of miles above sea level because of how much ice you're sitting on top of. So there's a long history of microwave astronomy at the South Pole, and in 2007, 2006, the South Pole Telescope was built there for just these observations, measuring the cosmic microwave background, this afterglow light. So it's this big sort of millimeter/radio wave telescope, 10-meter aperture, and that's what you need to find the particular wavelength that we're looking at, 2 millimeters, where this afterglow light from the Big Bang is brightest. Yeah, my background was observing this, trying to suss out information about the early universe and how that connects to the universe we see today.
So, as we sort of look at I'll call it how we know, or how we come to these insights. One thing that was surprising to me, I'll say early on, was the amount of I'll say extrapolation, data transformation required to get from the raw signals that we encounter at the measurement instrument, and when we can actually say, this is how we measure this, or this is how we resolve the picture of M87 or things like that. Just if you go through just kind of what you call your hit list of things that you look for and do when you're taking a raw data set. and turning that into insight. And the reason I'm asking is because next I'm going to ask about the Sophia in the sort of the water on the moon that's not in the permanently shadowed regions. But sorry, so go ahead.
Yeah. So the data kind of processing and analysis is a little involved. You have to realize that this light's been streaming through the universe for close to 14 billion years, and for most of that, it hasn't touched anything. Maybe 1% of the photons have gone through something. It's been transformed a little bit, but most of it is pristine. Hasn't been touched since it scattered off of whatever it last scattered on, 13.8 billion years ago, and then it suddenly hits our atmosphere, and that does stuff to it. Part of that is being absorbed. And on top of that, we're not just observing this light from the early universe. We're actually observing light that the atmosphere is emitting. Everything in the universe has a temperature, and because of that, it emits what's called black body radiation. So, human beings are emitting black body. We're just in the infrared. So the CMB, the cosmic microwave background, is of course microwaves. And if you were to convert that into a temperature, like what temperature is the light kind of corresponding to, how bright the light is? It's close to 3 Kelvin, which is just a few degrees above absolute zero. So it's very, very cold. And when you factor in like how the temperature of the air in the atmosphere and how much of that you actually interact with, that's more like tens of degrees. So the atmosphere is actually far brighter than the signal we're looking for. On top of that, you have issues like molecular lines from oxygen, from water, what water is left in the air. And so when you're observing, you have just huge signals from being here on Earth, and that's problematic. So the whole instrument, the whole experiment is designed to get around things like that. So unlike a normal telescope, you might imagine, or even just taking a picture at home, you might keep the aperture open for a few seconds or a couple of minutes or whatever, and slowly collect light, and eventually that's bright enough for the image you want. Millimeter wave telescopes don't do that. Instead, we tend to continuously scan. So we're never staring at one spot all the time. And the reason we do this is because if we did, then we would get this constant atmospheric signal. So by moving the telescope, we can actually upmix the interesting signal from low frequencies to higher frequencies in our data, and then we can filter out the low frequencies, knowing that that's actually atmosphere. And the interesting bit, the part that we're actually caring about, is at a higher frequency. Once you've done all that, then you have to take into account things like, you have to know where the telescope's pointing at all times. So it's not just staring at one spot. So you have to know every second where the telescope's pointing. Eventually, you can take all of that pointing information as you're scanning across the sky and build a map out of that by collecting all the raw data and bucketing into little pixels. But you have to know where the telescope was pointing. Of course, you told the telescope where to point, and that's not necessarily where it was, because it's deforming because of wind or temperature and all sorts of things. So you have to take it into account, things like that. And then you have to take into account, and this is across astronomy, how the instrument responds to a light source. So you might have an infinitesimally small dot on the sky that you're trying to observe. And if you put that light through your instrument, through your telescope, you won't get a dot. You'll end up getting some sort of smeared out blob. And that's kind of how your instrument responds to tiny inputs, tiny pinprick inputs. So we have to understand that. Basically what that means is, if you're looking at really tiny features in the sky, those get smeared out because you can't see, you don't have infinite resolution. So you have to back that out of your data. You have to say, okay, I know that there might be high frequency information there, spatial information, something that's really, really small in the sky, but my instrument's smearing that out. So you have to back all that out too. So it's a long process of actually getting down to like high quality science grade data. But once you have that, you can do amazing things.
So, so speaking of which, I don't know if you've been able to study what, sort of the sort of how they came to the information about how we know now that there's, possible water molecules, however disparate, actually in the areas of the moon that we originally thought was impossible, because apparently it's entrained in glass. Just, curiously, from just a general, just a general, like, I'd say, up until that, Sophia, we really thought that everything, all that was hydroxyls. Sort of, how do you how do you think, how do you go about, sort of, eliminating all of the different, I'll call it, how would you go about looking at that data set and thinking about, I'm kind of a dumb question, but I'll go with it anyway.
No, I think I know what you mean. Yeah, I mean, so when I first heard about this, I thought, well, that's pretty cool, and it's doing a slightly different technique than what we use on the South Pole Telescope, but it's analogous. So just to step back on looking at the CMB, what we end up doing is asking, how much variation on the sky is there at various scales? So if I were to compare big blobs on the sky, how bright are those compared to each other, and get some sort of power measurement, variance measurement. And then you look at very smaller scales, compare all the different blobs that are slightly smaller, and look at the variance in that. So we're getting a spectrum of variance across spatial scales. And what Sophia did, and what's common in other subfields of astronomy, is instead of breaking the light up into variations across the sky, across the patch, they're breaking it up in color. So they're doing the same thing, but instead of spatial frequency, they're doing it in like light frequency, the spectral frequency of the light. So that's connection there. So they're breaking things up and asking how bright are things at different colors. And they're using the problem for us, which was, there's molecular lines from water. Our trash is their signal, right? So they're looking at that and they're saying, what do I see absorption lines from water compared to hydroxyl? And my understanding was they had seen hydroxyl before. I think it was some complex of lines at 3 microns or something like that.
Yeah.
And this new measurement was at 6 microns, which was something that they weren't able to do before, which is more securely connected to water than something else. So questions I might have is, Sophia is cool because they fly way above most of the atmosphere, which has similar problems. Same reason we go to the South Pole. They want to get above a lot of the water, above a lot of the atmosphere itself, so it doesn't affect the signal. There's still some water left, so I'm sure they're doing things like taking some sort of baseline measurement and saying, okay, this is our background. We have to remove this because that's from the atmosphere, our atmosphere, not what we see on the moon. And then, when you look through those kind of details, and then you're like, okay, how sensitive is the signal? And I have a whole bunch of relatively low significance detections, but combined, it ends up being pretty compelling. But yeah, I think it turns out to be something like 12 ounces of water per cubic meter of sand. It's quite a bit in an area that's usually covered in light, or often covered in light. That's pretty remarkable.
Yeah, I thought that, I thought that was crazy. In space resources, we were effectively taught that it was impossible, that the water would not sublimate if the sun hit it. And so that has a couple of interesting implications. One is that there are situations in which the water can survive the sun, but two, that means that all those areas where we thought the only place it was were in the craters, where it could accumulate over millions of years, it could also have accumulated over millions of years so there's orders of magnitude more water likely on the lunar surface than we thought. How easy it is to get to is another question. But based on just this kind of this, I guess I'll just kind of ask, what to you is the most interesting, like, what, so what kinds of things would you like to study? So let's just say that we got to a point where we could start putting, I'll say, telescopes for the radio, otherwise, on the moon. What types of things would you like to study with that kind of,
Yeah. There's a really interesting. It's a relatively young field, all about that measures 21 centimeters. So this is the hyperfine hydrogen line. So it has to do with the electron and spin and the nucleus, the proton spin being either aligned or anti-aligned. And when they find the lower energy configuration, it spits out a photon, which is 21 centimeters, 1.4 gigahertz, give or take. So this is an ubiquitous signal throughout the universe where there is neutral hydrogen. And for much of the early history of the universe, before stars started turning on and generating UV light, which is strong enough to rip hydrogen apart and ionize it, the universe was nothing but neutral hydrogen, slowly clumping with gravity. So this is kind of cool, because if you can measure the 21 centimeter, you can actually map out distributions of gas before there were stars and galaxies in the early universe, and actually look and see how it clumps, and kind of look at this in shells. You can see doing tomography, how much mass is there in this shell close to me, this shell farther out, until you get to the point where you can't see any further, which is this afterglow light of the Big Bang, cosmic microwave background. So you can actually do similar science as what the CMB does by looking at variations in temperature and brightness across the sky in the CMB, but do that with variations in hydrogen, neutral hydrogen across the universe. The tricky thing with that is that 21 centimeters is pretty long, right? 1.4 gigahertz is, that's this, right? that's a huge wavelength, fat photon. It's still pretty high frequency when you think about it. But as you go farther out for Earth, the photon's been traveling longer to get here. And as the universe has expanded, that photon's wavelength has redshifted. It's gotten longer. So you end up with the regime where most of the neutral hydrogen exists in the universe before stars and galaxies existed and ionized everything, and then that signal turned off, is redshifts of factors of a few to 10 or 20. So and that's the redshift, for those that don't know, is the factor of how much the universe has expanded. So redshift today is 0. So a redshift of 1 would mean that the universe's radius has doubled. Since redshift 1. So the higher the redshift, the further back in time you go. So if you're looking at 21 centimeter that was emitted really early on, when there was nothing but neutral hydrogen, you're talking at wavelengths that are several or tens times longer than 21 centimeters. And now you're getting into the region where it's just totally destroyed by human radio signals. So there's only a handful of places you can attempt to measure this on Earth. South Africa, maybe Western Australia. Maybe, you could do it in other places that are more remote, but then, you still need the infrastructure to do it. So it's very, very hard. If you could put an array of radio telescopes, or in this case, just antennas, on the far side of the moon, at least during the 2 weeks of the month that the far side isn't facing the sun, you would have a totally blocked, totally clean radio view of the sky. Because it turns out to really map out this hydrogen, all the interesting redshifts that correspond to longer wavelengths are just right in the middle of communications and TV and all the nonsense that we do.
Right.
And the only way, sorry, go ahead.
No, yeah, go ahead.
Yeah, the only way to do this science is to get away from humans. And the best place we have is the far side of the moon. So that's just kind of, that would be a holy grail. Because we've done, hearkening back to the CMB, we've done so much science, we've learned so much about the early universe by just looking at this outer shell, as far out as you can go, you see this like wall of fire, which is the afterglow of the Big Bang, but you're really just looking at a snapshot of the universe, just that moment. That moment was maybe 100,000 years long, but from our point of view, it's this tiny thin shell, and you can learn a lot from that shell. But what if you filled in the whole sphere of observable universe with information about all the matter? Then you can do the same analysis that you did on the CMB on every shell, but also in this direction too. So you can do like, you take the Fourier transform, look at modes of what's going on. There's these variance changes in intensity, not just on the sky, but through the sky. And so there's like, a trillion more modes available to measure through 21 centimeter than the CMB has to offer. So it's just an enormous amount of information. So it'd be huge to do that.
So, speaking of which, and I'm generally curious, we've used very long baseline interferometry for a lot of things. I'm curious, is the potential of having a sort of, I'll say, a synced, radio telescope to some telescopes we have on Earth, are there any implications from your perspective to having I'll call it a receptor source so far away from the rest of them that we have here on Earth?
Yeah, there's some things you can do with it. So, to be clear, any sort of radio telescope that we put on the far side of the moon would end up being basically an interferometric array. It'd be a whole bunch of antennas that are communicating, and then what's really happening is like every pair of antennas is measuring one Fourier mode for those, who are comfortable with that. So the more modes you have, the more pairs you have, the more you can fill in that spectral space and then get an image out of this. So, and then of course the resolution you have is inversely related to the length of the distance between the pair of antennas. So if you had a single antenna on Earth and a single antenna on the far side of the moon and had some way to communicate with them, maybe with a satellite around the moon, then that's like 100 times the baseline that we could have on Earth, right? That's huge. So yeah, you can get 100 times the resolution. The tricky thing then is that you really only have that one long baseline. So you're only filling in a couple of modes, but you can still do some interesting stuff with that. I know I saw that, there's the Event Horizon Telescope, which was that interferometric array that measured got the first image of gas falling into a black hole, right? Or more or less that view. If they were to extend their network to include an array on the far side of the moon, then they would get that extra factor of 100 resolution. And instead of having this smudgy image, well, you wouldn't have enough modes necessarily to get a nice image, but you get like a kind of a cross-section view. That smudgy circle would end up being a very crisp circle, and you can actually start doing really interesting tests of general relativity by looking at the width of that circle and its intensity and interesting things like that. So who wouldn't love a telescope effectively the size of the Earth-Moon radius?
Well, and curiously that, theoretically we could fill in additional modes like a telescope at Earth Moon Lagrange point 1.
There's tons kind of farther out there. I mean, not technically impossible, but harder to do things.
Right.
And even having just a handful of arrays, you can say, well, I can look at the pairings between all the antennas on the far side of the moon with all the antennas on Earth. But the difference between those isn't all that. It'd be measuring basically the same modes. Mm-hmm. But yeah, there's other ways to do it, right? You can put satellites up at other Lagrange points. You could put up, anything, right? You could put stuff around the other spots as far out as you want to go. It just becomes more and more challenging to do the correlations. You have to get that information back, do the correlations, have the timing all synced up perfectly. But yeah, I mean, there's tons of stuff you could do. It's really interesting.
Well, I mean, so I'll tell you, what I'm going to do right now is I'm just going to let you, is there anything that's just really exciting to you right now, just in general, that you just kind of want to you just kind of want to talk about, because the truth is your expertise in this is so far out there that I don't even have good questions for you.
Sure. I mean, sure. And, you know, I am definitely adjacent to, you know, in situ resource utilization, right? Like it's not something that's not my wheelhouse, but being able to do things from space is, it's really such a big improvement. I guess going back to my wheelhouse, the cosmic microwave background, you know, there's so much interesting stuff you can do with it. And we're, again, totally limited by the atmosphere on Earth. You know, like I mentioned it earlier, these photons have been traveling for the age of the universe, and they almost reached our telescope, almost there, you know, like literally a split second away, and they get absorbed by something in the atmosphere and we don't get to see it. And I think that's kind of sad, you know, like, why don't we get to absorb that? So of course, you know, the next thing was, well, why don't you put something in space? And scientists have, right? There have been 3 big generations of CMB telescopes in space. There was the Kobe experiment in the early 90s, WMAP in the early 2000s, and then in the late 2000s, early 2010s, Planck. And they were able to do far more than what you could do from the ground with a smaller telescope, because instead of, you know, like our instrument had, the version of the camera that I worked on had 1,000 pixels, something like that. Planck had 10 or 20, like 20-ish pixels, on, you know, an order of magnitude fewer, or 2 orders of magnitude fewer. I can't do math. Yeah, anyway, roughly 100 times fewer pixels than us. And they were able to get, just do incredible science across the whole sky, because they had all the space to use. So you can do that on the moon too, right? Like you can do this from the far side. And there you kind of get the best of both worlds. So on Earth, you can have really big cameras because you have this nice stable ground, more or less stable ground to build a big telescope. So you get higher resolution too, because you can build a, 10-meter telescope. Space, it's expensive to put up a really large satellite. So Planck does really great because there's like no signal from the atmosphere, so they can get away with a few pixels, but they're stuck on resolution. But if you put it on the far side of the moon, then you can build something relatively big and have a huge camera in it, and have the best of both worlds. And it's not like Moon isn't totally stable. It's got moonquakes, and if you 2 weeks of just punishing sunlight and then 2 weeks of punishing darkness. So you have to deal with deformations in the actual instruments and things like that. But at the wavelengths we're looking at, like 2 millimeters, it's pretty small, but it's still pretty big, and you can get away with pretty large deformations and be able to account for that. Much harder to do it like optical or UV wavelengths, where you just have to have you have to know the structure of the telescope so much better. I mean, going back to 21 centimeter stuff, it's even longer wavelength. The longer the wavelength, the easier it is. Right? Like there are experiments on Earth, like Paper and Hera, that are literally built with like chicken wire and PVC piping, because you can get away with that, and that's all you need. Like engineering, all you need for the signal at 21 centimeters. So yeah, you can get the best of both worlds by doing CMB science from the other side of the moon. And yeah, I mean, I could go on forever about CMB.
Right. Well, what I'm going to do is.
Thank you for listening to the Friends of Space Resources podcast, and welcome. Connect with us on social media by searching the Friends of Space Resources podcast, and join us online at friendsofisru.com. Check back weekly for new episodes and new insights into space resources. Until next time, look up and keep dreaming.